Okay, everybody, thank you so much for just waiting those extra few minutes for us. We had a couple of people coming in. We want to make sure that everybody who intended to listen was able to start with us from the beginning. So I want to give another healthy good morning to everybody and a welcome to today's webinar. This webinar is on GE's Innovation Challenge, Alternative Manufacturing of Aviation Castings. My name is Casey Shapiro, and I will be your host and moderator for this webinar. So there's going to be 5 parts to this webinar, and now we're going to briefly go through the agenda. First, we're going to provide speaker introductions, and then we'll provide an overview of the challenge. After that, we'll then present frequently asked questions of the challenge, and then we'll work through a live audience Q&A. To go ahead and participate in this Q&A, please submit your questions at any time through the Q&A chat box through the WebEx platform. We will collect and then present those questions during the live Q&A section. If we don't answer your question live, please note that we are transcribing and then answering all questions asked during the session and then posting them on the challenge forum for viewing at a later date. And then finally, we'll wrap up with some information on what you can do today for the challenge, including where to register, how to stay connected, and then also how to submit your proposal. So moving on, I am now pleased to welcome the following speakers to our webinar this morning. From GE, we have Lisa Ralph, Open Innovation Operations and FastWorks Integration Leader, and Neil Gray, Principal Casting Engineer, Structural Castings. And then from 9 Sigma, we have Pam Semanik, Program Manager. So again, the topic of today's webinar is GE's Alternative Manufacturing of Aviation Castings. 9 Sigma, representing the General Electric Company, seeks technology proposal submissions for manufacturing methods as an alternative to investment casting of aviation parts. And now we're going to go ahead and hear from Lisa Ralph on GE's vision and goals for this challenge. 1 second. Okay, Lisa, I think you're all ready to go.
Perfect. Thanks, Casey. So good morning, everyone. Thank you so much for joining. We are thrilled that you're here. My name is Lisa Ralph. I am our Open Innovation Operations and FastWorks Integration here at GE Corporate in our Open Innovation Center of Excellence. So that's a lot of words, but what I really do is look to scan the landscape both inside and out of GE to codify our best practices and processes, as well as manage a diverse set of campaigns across our portfolio on a day-to-day basis. So open innovation is something that is new for us here at GE. The mere thought of reaching outside our walls a couple years ago was something that was crazy, but it's still novel, but it's something that is incredibly intriguing and something we are so excited to kick off. It's really allowing us to collaborate with brilliant people just like you guys on the phone and here on the WebEx and really work on some of our highest value problems. So it's throwing the status quo out the window and really, again, allowing us to perforate the walls of our previous constraints and reframe what's possible. And so what's important to really underscore there is the fact that we're not just looking for ideas. The entire reason we're invested in this is outcomes. We really want tangible outcomes and to be able to bring these ideas, proposals, etc. to life. And here with GE, so your ability to work on these really challenging priorities of ours is so helpful because it's allowing us to look through a new lens on these great problems, and it's impactful because it's in collaboration with GE. The potential scale of implementing your solution is huge. I mean, we're talking across our industrial businesses. We're a conglomerate, so there's a ton of opportunity for cross-pollination at huge scale, just in terms of volume. We do make a lot of stuff, so it's great there as well as across the globe. We're actually in over 170 countries. So what I personally think is neat about this collaboration and why I'm glad you guys are here is that because of this massive scale, because of your great ideas, and because of this global footprint, that your solutions can literally be impacting and improving the lives of hundreds, if not hundreds of thousands of people all over the world. So really, again, this is a great opportunity to partner together on some of our toughest challenges. And then the core of this is really a charge to develop better more efficient outcomes so that we can define tomorrow today. So that's I would say, 500-foot view of what we're doing with open innovation at GE, which is good to know, but let's say, how do we take this down a notch? How do we make this happen? And how can we make this more tangible? So why we're here today is for our alternative manufacturing of aviation castings challenge. So as I mentioned just a moment ago in our last slide, open innovation is something that we are selectively choosing to apply to our toughest, highest value priorities. So alternative manufacturing of aviation castings. Why is this one of them? To start off, let's just talk pure scale of impact. GE Aviation has a huge installed base. We had, I believe, around 33,000 commercial engines in operation in 2013, and that number is growing at a steadily increasing rate. So that's thereby increasing pressure to increase output on our end within the same resource constraints, which was really driving and inviting this need for new technology, which is why we're here today. So it's important to note, too, that these aircraft production is something that is incredibly complex. It's incredibly demanding. Currently, our components are precision crafted to very tight tolerances, as noted here, and we actually individually inspect each component for compliance. So that's a lot of work, as you can imagine, given our large and growing installed base, but it's also something that is hugely important, especially when accuracy, quality, and compliance are all non-negotiables in this industry. So we're here today. We are seeking new methods, new processes, and new technologies that can really help expedite the process of manufacturing while maintaining these equivalent life capabilities. So this is really important and exciting to us because these kind of new advancements really have a huge opportunity to save hundreds and hundreds, if not thousands, and we will have the technical team correct me if I'm wrong, but it has a huge impact on the production cycle. And additionally, I think what's interesting for you guys as well, that this is specifically an alternative manufacturing of aviation castings challenge. But what's at the core of it is that it's really a search for new processes and new technologies for casting. And we're starting with one casting, but as you can imagine, there are quite a few parts within the world and realm of aviation, and that number is continuing to grow. So as your solution has the potential to completely redefine our casting process for GE. That's not only for this specific casting, that if you viewed this challenge in advance, you'll see we've called out a specific part, but those technologies, methods, processes have the potential to be applied not only across our aviation business, but also, again, calling to that cross-pollination across GE's industries. So manufacturing and industry, those are our lifeblood at GE. And compliance, that's the lifeblood of GE Aviation. So here in this challenge, what's neat, I think, and what's super exciting is you have the chance to really define real outcomes that can really be used and set a new bar for one of the most important facets of GE Aviation.
Great. Thank you so much for that, Lisa. Now we're going to go ahead and turn it over to Neil for some information on the technical goals of the challenge. Neil, I think you're all ready to go.
Okay, thank you. And thanks, Lisa. I think everybody got a really good view of where overall from a GE standpoint we're looking at this process, and I'm really happy to be involved in it. I've been working on structural castings here at GE for quite a number of years, and I'm excited to have all of you involved now in looking at some alternatives for us. So we can talk a little bit about structural castings, but GE is a longtime user of structural castings in the aviation and land-based turbine business, and for the most part, I would say that we've been very successful with that. But we've come to the conclusion now it is time to evaluate emerging technologies and process improvements that would give us potentially lower cost and possibly reduce variation in the products that we have. And the goal of the challenge really is to identify what processes we could potentially adapt to produce product that would give us equivalent life and capabilities at a lower cost, and preferably at a slightly reduced cycle time and with reduced dimensional variations. And to expand a little bit about that, we've been using castings extensively on engines for years and years, and they've grown over the years. I've been here for about 30 years, and the number of castings that we've used from the early engines to what we're producing today is significantly different. I mean, the number of them has expanded a lot. So I think what we're looking to you for part of the goal is to expand our vision on how parts could be manufactured. Do you have ideas that we've not considered, or maybe we didn't think would work? And cost is a significant driver for us. It's a significant measurement for us and our customers, as well as customer value. So higher cost without a higher value to our customers doesn't provide any gain, and so we are forced into trade-offs. So we are looking for, what kind of things could you propose to us that would reduce cost but give us equivalent value? And I think that's important for us moving forward. Go ahead, Casey, go to the next slide. Okay, so this is the product we picked, and Lisa kind of gave you a little snapshot of this. This is a typical part that we would use in an engine. It's a bearing housing, and we have a number of these in slightly different shapes across a number of engines. So this is an opportunity for us to pick a component like this, but certainly we see applications potentially in similar type products across the board on a number of engines. So we don't want to flood you with a whole bunch of parts. This is just an example part that's pretty typical for us. And this shows a brief cross section of the engine, but this part is a bearing housing, and its main function is to hold the bearing in position. The bearing supports the shafts that run through the engine. And the primary function of this part then, in addition to holding that bearing, is to provide oil into that housing to spray on the bearing for lubrication. And then the housing captures the oil and routes it back through the supply system and recycles it. So I'm going to apologize. I believe on the initial information, we identified the material correctly as 17.4 pH steel. Unfortunately, I think the first thing we sent out was I gave the wrong AMS specification number. I gave the one for 718, and I apologize for that. But the actual material for this particular part is AMS 5355, which is 17.4 pH. And it's selected for a variety of reasons. Obviously, its tensile strength and its cyclic loading capabilities at temperature are important. This material is a little lower cost than some of the more expensive nickel-based alloys, and its thermal expansion compatibility with the bearing materials is important. Alternate materials can be evaluated. I know we've had some questions about that. Would we look at alternate materials? The answer to that is yes, but we would ask you to at least look at and make a consideration for how it would compare with AMS 5355. And obviously, I mean, most of you are going to understand that this thing is made from stainless steel. Please don't propose aluminum, because I'll tell you right now, it's going to operate at temperatures that are much higher than it would tolerate in aluminum. So we would just note, initially take a look at the material, and if you want to make a proposal for a different material, that would be fine. But at least make it in line with the strength requirements of something along the lines of 17.4 pH. And I apologize for the confusion about the material spec. We have corrected that now, but just wanted to point that out. Okay, Casey, go to the next slide. So just to give a broader view, this is what that subassembly bolts into. This happens to be the rear frame of the engine. And the subassembly then is bolted into the center section of this to hold it, and then the frame provides the remainder of the support to the bearing housing, and as it addresses the entire engine. And ultimately, what happens is that through the struts, the oil is introduced down to that bearing housing. So there's a path in and a path out for the bearing, and that's what the frame, part of what the frame is doing then, is providing those entrance and exits for the part. And so you can see that it's a whole component then, and we are just looking at a particular segment of that component. Now, obviously, the operating structure of this gets kind of complicated. The loading can be very complicated, and so we're just asking you to look at 17.4 as a baseline. There is a little better concept to look through, expanded if you're going to look at manufacturing overall. I mean, in theory, it would be possible to add other components into this, and we would ask you to identify exactly what you're proposing to produce, and then we would have to evaluate the proposal for impact on the overall product. At this point, we have not really provided enough definition to you to look too deeply into process optimization, like joining other components to the part we have. But if you see that as an option, I would suggest that you point that opportunity out, and we will consider that as a follow-on change to the product. Evaluating the function. One of the things we did provide to you, and I believe there was a question on, was the profile tolerance we have on this part in general is plus or minus 35 thousandths of an inch. So that's what we live with today on the product. If you can produce that at a little better level, that would be good. One of the things that we would be interested in for a long-term goal would be, can you control the wall thickness of the product better than what we do on a normal casting? And these castings usually have about plus or minus 15 thousandths on wall thickness control, and those tolerances drive weight onto the product. And anything that we can do for weight reduction, if you can control the wall thickness to plus or minus 5 thousandths, then there's an advantage for us to look at product weight improvements, which would be important for us where we can thin down and still tolerate the strength issue. So that would be another thing to consider for us. So there are a number of issues that we're looking at. It's a goal for flying product, obviously, to reduce weight. The less weight in the engine, the less weight you have to lift off the ground. So that is a long-term goal for us as well. Can you go to the next slide then, Casey? We wanted to make just a quick rundown of the casting process, just so people would understand it. For those of you who aren't familiar with it or haven't seen it, the wax is injected into a die, and sometimes there are several injection processes that go together to produce a product of this complexity, one for the internal part of the component and one for the external part of the component. Following that, there's a cleaning process that's done prior to after the final wax injection. There's a cleaning process to remove die lines and any imperfections in the product, and then the pattern moves on to an assembly operation, and where all the feeding lines for metal introduction into the part, the gating system, is added on, and then part of that provides structural support for the mold so it can go into the next operation, which is the ceramic shell building operation. And the ceramic shell build operation can put stresses on the part itself between putting it into the ceramic and putting the powder on. So there's a strength component into that the supplier sometimes has to build onto that component. So this goes through a number of steps. Following the completion of all the layers that have to be added on, there's normally a drying period to eliminate the majority of the moisture that's left over. And from there it goes into a wax removal operation and normally that's done with a high-pressure steam autoclave, though different suppliers have options to use different methods. And that's usually the mold is put into this high-pressure steam autoclave. The steam is introduced. Obviously, it's at very high pressures. The heat penetrates the shell material quickly and rapidly melts the wax out before the ceramic, before it gets a chance to expand against the ceramic and crack it. So following the wax removal operation, any cleaning that's required is usually done to the mold before it moves to the foundry operations, which then usually take over heating the mold to the proper temperature prior to pouring. And once you get the metal introduced, then there's a series of labor-intensive operations to remove the gating from the part, and we tend to lump these operations under finishing, what we call a finishing operations, and those are, removing the part from the gating, which is usually done by a cutting operation of some sort, and then cleaning up all the parting lines that may be left over that weren't removed in wax, any excess material, and rework of any imperfections that are in the part. For materials such as what we're talking about here, 17.4, there are normally a number of welding cycles to fix flaws in the castings. Following that, the part will go through a heat treat operation, in this particular case, a standard homogenization, solution, and age cycle. And at the end of the process, there are usually final non-destructive testing operations, usually fluorescent penetrant and X-ray inspection for castings, as well as dimensional inspections to validate that the part conforms to the drawing. Now, as you can see in the process, it's a little more complicated than just this flow chart. There are a number of operations that kind of fall in underneath those headings, but the cycle can take up to 12 weeks for a part like this, depending on the rework level. All this time usually translates into cost, unfortunately, and from what you see today, the challenge is to identify a process that can give us a part that would still meet all of our life requirements at a lower cost than the casting target cost, and preferably with a shorter cycle time. Regarding the cost, we proposed a volume of 125 pieces a year as a baseline. Ultimately, we want the production cost to be below what the casting target is. But obviously, for the first X number of pieces, we understand that's not always possible. And we understand that the initial pieces may cost a little bit more. We generally call that learning curve pricing, and we anticipate that the price goes down as the process matures. So the mature price is really what we're after. So that's kind of the goals of where we're going to with the process. Pam, do you want to take over then?
Yes, thank you so much for that, Neil. We're going to go ahead and move on to the challenge FAQs. These are the questions that are commonly asked during any type of challenge like this, or just in general about this specific challenge. We're going to go ahead and move on. So the first one, when is the deadline to submit an entry?
So this is really exciting, and we really appreciate your interest and participation in this Open Innovation Contest. Please do, though, submit your entry before January 28th. That is the deadline for this Innovation Challenge.
And how do I submit an entry?
You'd go to our website, the 9Sites platform. The link is included here, and you would submit your entry directly online through that platform page.
So number 3, what should I include in my entry?
We're really looking for a clear and concise description of your proposed approach. As Neil said in his description of what he's looking for, if you can justify some of the changes that you can propose to the manufacturing based on, how it differs from current casting, that would be really helpful in evaluating that technology. So we would like specific information to address the data set that's included in that challenge content. So if you go to the website, you will see all that information there.
Great. And then number 4, when will GE announce the winners?
GE is assembling a panel of experts to evaluate all of the entries, and we anticipate the announcing of the challenge winners in April of this year.
Great. So the last challenge FAQ, what is the size of the part referenced in the challenge description?
At its largest diameter, the part is about 15 inches and 7.3 inches in overall height, and the weight of that part is approximately 63 pounds.
Great. Thank you so much for that, Pam. Now we're going to be moving on to the live Q&A portion. At this time, we'll be opening the session up to any of the questions from the audience, so please continue to submit those questions through the Q&A chat box. We'll take the rest of this time to answer those live. Again, if we don't get to your question, don't worry. This Q&A session is being archived, and then all of the questions and answers will be made available on the challenge site, including the recording of this webinar following it. So we're just going to go ahead and get started on the live questions. So the first one that we have is, a goal is reduced dimensional variation. What is the expected goal from this reduced dimensional variation, and how would GE make use of that improvement?
Do you want me to answer that, Casey?
Yes, please.
Okay, I had mentioned that briefly, but to us, dimensional variation tends to add weight. And so one of the goals we would have for reduced dimensional variation is if you could control feature sizes and positions closer, we could reduce the amount of added material on the part. Now that allows us the advantage of removing weight from the component, which